I stopped, I didn't record right away. So we have, of the 5 billionaires in California, they have this many children, 1, 2, 4, 4, or 7. Move this over a little bit further. We have this many possible children. So if we took every sample of size 2, this is what we're going to get. So that's X bar 5, X bar 6, X bar 7, X bar 8. We have exactly 10 X bars because there's exactly 10 samples. Okay, so what are my sample means? I think we could all do this without a calculator. I don't know, can we? What's the mean of 1 and 2? Walk me through it. What's the mean? Maybe we can't do this without a calculator. Yeah, 1 plus 2 over 2. I think you guys can do this in your head. God, I hope you can do this in your head, because if you can't, we're really in trouble. We're in big trouble. The next one? 2.5. The next one? The next one? I'm gonna put 4.0 just so consistency that we see each one is like this. What's the next one? 3.0, 3.0, 4.5, 4.0, 5.5, and by the way, we said if we just simply took the 5 billionaires and added them up and divided by 5, we got 3.6. So we already know that's the answer. Do you see 3.6 on any of my samples? No. So in reality, a sample mean may not be what the population mean is. Not your one sample mean. But are all of these not crazy far off, maybe? I don't know. Now, we're going to do something kind of crazy. I want to find the mean of all of these values. Now, this is kind of interesting. Let's take all of our sample means. Do you agree that this is every possible sample mean we could possibly have if we did a sample of size 2? Let's find the mean of these. So what I want to do is add up all of these numbers, 1.5 plus, 2.5 plus, 2.5 plus, 4.0 plus, 3.0 plus. Okay, I'll keep going. 3.0 plus, 4.5 plus, 4.0. Let's add up all these numbers. And what will we divide by? Well, how many are there? 10. Add all those up and divide by 10 for me, please. Do that on your calculator. Let's find all of our sample means. Well, we found all of our sample means. Let's find the mean of our sample means. And we have a name for this. We actually call it, you like this, it's mu of the X bars. And we put X bar as a subscript. Mu is the mean, period. But I want to find the mean of my sample means, which is a little bit different. Now, nobody in real life is going to do it this way, but I'm going to show you something really cool about how I go. So 1.5 plus 2.4. So when you added up the numerator, it should add up to 36. Is that what you got? And then when you divide by 10, what'd you get? 3.6. Huh. Gee, what a weird coincidence. When I considered every conceivable sample mean of size 2, and I found the mean, I got the same thing as the actual mean. This is actually really, really important. This is what is called the central limit theorem. And I'm just doing a demonstration. I'm not doing a formal mathematical proof. Whatever the mean of a population is, it is what it is, and our goal is, if we can find it, we find it. But reality, I want to find the mean of human beings' heights. Yeah, that'd be kind of tough, huh? Because there's a lot of humans. and by the time I get done finding all of their heights, some of them might have gotten taller, right? Because it took me a really long time to find their heights. So we don't try to measure every human being. What we do is we take a sample of human beings, we find their average height, and then use that to estimate the whole. That's what the whole point of samples are. But here's the cool thing. If you considered every conceivable sample, take any population, now think of every sample of a particular size. So we could do the same problem by taking samples of size 3. We could do the same problem by taking samples of size 4, and so on. If you consider every conceivable sample of a given size, find the mean of all your samples, and now find the mean of all your sample means. It'll be exactly the same as the population mean, but less spread out. the sample means are a tighter fit. And so if I know that the average of all possible samples is still going to give me the actual mean, then the bigger the sample, the more likely it's going to be close or even right on. Does that make sense? The bigger the sample, the better it's going to be. So I want to do this problem again, but this time I want to do samples of size 3. So I just did every conceivable sample of size 2, and we got exactly the sample mean. But notice the spread of these. It went from 1.5 to 5.5. That was the spread of my sample means, which, by the way, is that a tighter spread than 1 to 7? Yeah, 1 to 7 is a little bit more of a range of values. 1.5 to 5.5 is a little bit tighter. So I want to do the same thing, but now I want to do samples of size 3. So we've got to kind of be mindful when we're writing them down. And by the way, exactly how many samples of size 3 will there be? There'll be 5 choose 3, which is also 10, by the way. That's why I'm doing this, because it's not that big. It's not that many. All right. So my samples of size 3 would be 1, 2, and 4, the first 3, then 1, 2, and the next 4, and then 1, 2, and 7, right? Boom, 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 boom. Then what? Then these 1, 4, and 4, the first 4 with the 7, and then the second 4 with the 7. Now I have 2, 4, and 4. I have 2, 4, and 7, and then 2 in the second 4 and 7, and then finally 4, 4, and 7. So I went these and these and these and these and these and these and these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. Now I don't want decimals because I'm going to have thirds. So let's just write thirds. Okay. So what is the first sample mean? So my first sample mean is 1 plus 2 plus 4 is 7. So 7 thirds, that's 2 1/3. My second sample mean is also 7 thirds. 3 plus 7 is 10. So my third sample mean is 10 thirds or 3 1/3. That's 9 thirds. 9 thirds is exactly 3, of course. 1 plus 4 plus 7 is 12. So my fifth sample mean is 12 thirds or 4. This is also going to be 4. 2 plus 4 plus 4 is 10. So this sample mean is 10 thirds. 2 plus 4 plus 7 is 13. So this one's 13 thirds. 2 plus 4 plus 7 again. That's 13 thirds. And my last sample mean 4 plus 4 plus 7 is 15 thirds or 5. Now, notice the range here. My smallest one is 2 1/3. My biggest one is 5. Is that a more narrow range than previously? Yeah, see the range is getting tighter, isn't it? As my sample gets bigger, the spread of values is smaller. Now let's do what we did before. Let's find the mean of all of these sample means. So all you got to do is say this plus 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 this. Just add them up on your calculator. Okay. And by the way, you can do 7 divided by 3. Your calculator will keep track of it. Or you can use your fraction key, whatever you want. It's going to be something over 10 because I have 10 values. You got 36 on top? Just, okay. So here's again what I want you to see. If I took individuals only, we know the mean of the population was 3.6. There's only 5 billionaires in California. If I said, consider every sample of size 2, we wrote them all down, we found all of the means, and the range of values for the means was a little more narrow than the individual values. Now we did every sample of size 3. Different, but now this range is even smaller. It's only from 2 1/3 to 5. Meaning, if you went out and just randomly took a sample of size 3, you would probably be even closer to the actual value. Now, in reality, you're not going to take a sample that's the whole population. That in reality probably isn't going to happen. So the idea here is the larger your sample, the closer your sample mean is probably going to be to the population mean. Now, what determines your sample size? We've talked about this before at the beginning of class. There's 2 things that determine, you're going to sample, you want to find out things. I want to find out the average height of a Mesa College student, for example. Remember, day one of class, we talked about how would you do that? How would you position yourself around campus? How would you do all these things? And we realized, okay, different times of day, different places on campus, because we want to get everybody. You're not going to be able to get everybody on campus, but you could get a lot of people. Or I want to ask how people are going to vote. Or I want to basically find out how long my tires are going to last. There's exactly two things that influence your samples. Do you remember? Time and money. Time and money. Oh, because sometimes it can be really expensive. I want to find out how the brakes are working in the brand new Lamborghinis. Do you know there's only one way to test brakes in a car? You know what it is? It's called crash test. You ever heard of those? Crash test dummies? You don't, by the way, if somebody's putting an ad in the newspaper for, we need to hire crash test dummies, don't answer that ad, because don't be a crash test dummy is the dummy in the car. When they crash it, they see what's the impact on the dummy. The only way you can test brakes on a car is to actually crash the car. Well, Lamborghinis are really expensive, so I don't really want to test a lot of them because that means I have to destroy the car. So time and money influence how you're going to do your sample, how big your sample is going to be. The rule of thumb is you do as big a sample as you could possibly afford to, time and money wise, because you're going to get the best results. Yeah, Shane. Yeah. But I'm just saying, I'm giving you an example. If whatever you're doing is really, really, really expensive, you probably can't afford to do a lot of them. Okay. So the mean of all the sample means is always equal to the mean of the population. That's the first rule. Okay. So central limit theorem is the mean of the sample means equals the mean of the population. But what about the spread? Didn't we notice that every time I increased my sample size, the spread got more narrow? What's the number that measures spread? Not the mean, the other thing, the variance. Variance is what measures the spread. Oh, so as I increase my sample size, nothing changes. The mean of all sample means always equals the mean of the population. But the variance of my sample means gets smaller as I increase sample size. So here's the second piece of the puzzle. This is what the central limit theorem, this is what it's all about. The variance of my sample means, this is crazy cool, is equal to the variance of the population divided by n, where n is the sample size. Oh, so the bigger my sample, the less spread my sample means are. Why is this important? Because it means the bigger my sample is, the more I can trust it. Now I'm going to give you a simple example. All right, you want to find out the average height of a Mesa College student, and you're just going to grab 3 people at random. Well, what if one of those 3 people is the tallest person on campus? Is your mean going to be a little bit off? Your sample mean, is it going to be a little bit off of what the, yeah, you're going to say, gee, the average person at Mesa College is 6'3". That's probably not, do you agree that that probably wouldn't be a very good, but what if I grabbed 300 people and I included the tallest person on campus? With 300 people, is the tallest person on campus going to make that mean be crazy big? Because remember, I'm dividing by 300. No, that might not even affect it by maybe at more than a ½ an inch or something. Okay, so if I grabbed a ridiculously large sample, even if I had the tallest person on campus or the shortest person on campus as part of my sample, it's not going to have a great influence on the final answer. Do you agree with that? That makes kind of sense. If I wanted to find out average income and I only grab a few people and one of them's a millionaire, it's going to be artificially high. But if I grab 1,000 people and one of them's a millionaire, it really won't matter because I'm dividing by 1,000 in the end. So the larger your sample, the more you can trust that that sample mean is going to be close to the population mean. But the better part is the larger your sample, the less the values are spread out. So I'm going to show you a simple picture that kind of illustrates that. And we're going to assume for a moment, we're going to think, what if it's a normally distributed set of values? Okay, so I have basically, here's a real life population. And let's say this could represent human heights. And right here, this would be the mean. We haven't made it into a z-score yet. Okay, this could be human heights. This could be duration of pregnancies. There's a lot of things that act this way. If you said, I'm going to go out and collect a really large sample, okay, the spread of these is whatever the spread of these is. I don't know what the standard deviation of human heights is, but I think it's probably in the range of like 6 or 7 inches or something. Okay. I know that in duration of pregnancies, the standard deviation is 7 days, roughly 1 week. If I went out and collected a sample that was very, very large, here's what it actually looks like in terms of the spread. Exactly the same mean, but much less spread. Does that make sense? That's what this says. The larger the sample, the less the spread. That means, would you say if I'm grabbing an individual from this population, if I grab somebody here, then I got somebody at the extreme high end. Do you agree? That's probably not going to tell me a lot of information. If I grab somebody at the extreme low end. That's not going to be useful. It's like I want to find the average height of a Mesa College student, and I grab one person. Dangerous sample, right? Because they could be the tallest or shortest person. Now, I grabbed a very tall group overall, so I'm really far over here. I grabbed a very short group, but because this was a large sample, even the bad samples, we would call these the bad samples, right? They're not too far from the mean. And if I have n be larger still, there's even more narrow. So the bigger the sample size, the closer you're going to be to the mean, even if you have a lousy sample. What we would call a lousy sample is you didn't do it wrong. You want to find the average height of a Mesa College student, and your sample includes a lot of really tall people. We'd say that's not a good sample. You know, way too many really tall people. But if the sample was huge, it won't be that far off. I have a lot of really short people. But in reality, I probably have tall and short people that kind of balance out in most samples. Agreed? Is it possible that you did everything right, that you still have a really tall sample or a really short sample if we're doing heights? Is it possible you could still be off? Yeah, because there's so many samples, but the vast majority of your samples should be probably really close. So the central limit theorem says, rather than take an individual from a population and find the probability of an outcome, take an entire sample from the population. So the example we started the class with tires. We talked about tires. I want to find the average lifespan of tires so I know what to give as the warranty. You see, I bought a set of tires, I won't say from where, and there was a 60,000 set of tires, and at 30,000 they were bald. And I was not happy. And I went back and they said, yeah, we probably sold you the wrong tires for your car. So what they did was they prorated them. That's what they call it. They don't give me brand new tires for free, but they gave me brand new tires at a significant discount because I only got half the life on my first ones. Okay, you guys are probably all familiar with this in some capacity. It's called prorating your tires. Now, let's say I'm supposed to get 60,000 and I only got 59,500 miles. No, they're not going to give me a new set of tires. They might give me $1 off a new set, right? Because I chose to get them rather than go that last 500 miles. But if the tires wore out prematurely, like very prematurely, they're going to do right by me. Most places that sell tires do this. But again, where the heck did they come up with 60,000 miles as being the average life? They had to test a lot of tires. They didn't test one set of tires. They probably tested hundreds, maybe even 1,000 set of tires. Does that mean that they threw away some money? Well, yeah, but that's what you have to do in real life. It's called research and development, R&D. You have to actually spend money to try things to see if they work, because then you're going to turn around and sell 1 million tires. If my tires are not good and that company has to replace my tires, they're losing money every time they do that, don't they? So they got to be careful with their warranty, what they're going to do. So they want to do all of the research necessary to say, hey, here's how long our tires should last. Because when you're shopping around, right, you look and say, well, these tires cost a certain amount of money, and that place says that I get 40,000. These tires cost roughly the same amount of money, and that place says I should get 60,000. Is that kind of a no-brainer what you're going to do? Yeah. Oh, so in reality, the 60,000 mile tires should cost more than the 40,000 mile tires because they're lasting longer. But that isn't always the case. And so how would I know I have to do really large samples? So if this is the case, then what is sigma? What is the standard deviation? Well, isn't sigma just the square root? So it'd be the square root of sigma squared over n, which is sigma over root n. Oh, this is a major, major formula. Why do I need this? Because in the calculation of a z-score, we use sigma, not sigma squared, correct? So here's the new formula that we're going to use. Because now we're not going to look at just individual scores, we're going to look at entire samples. So for an individual score, I'm going to write it down real clear. For an individual outcome, Z is equal to score minus mean over standard deviation. Okay, that's what it is. That's what we've been doing for many weeks. For a sample of size n, Z is equal to the sample mean minus the mean of the sample means over the standard deviation of the sample means. Okay. Is it basically the same formula? Yeah, but instead of one value, I have a whole bunch of samples. But what does that equal? Well, we already showed that this is the same as mu. But this, oh, that's different. So the only thing you're going to do different in your calculation for Z is that you have to have that guy. Now this is kind of a simple way of thinking about this. So are there two completely different formulas going on here? No, actually, they're really the same formula. Because if it's an individual outcome, what is N? For an individual, what's N? 1. Have you ever heard the expression sample of size 1? That's not a good sample in general. But can you have a sample of size 1? I only had time to ask one person what they thought. Yeah, a sample of size 1 would be an individual outcome. So if I have an individual outcome, wouldn't that N be 1? And then am I using this formula? Yeah, I actually am. And my X bar would be my X because I only had one thing. So this formula here actually is the same as this one when N is 1. You'd get the same formula. So don't divide by square root of 1. That seems kind of silly. So let's do an example of this. Because I want to contrast and compare to show you things. So let's see, let me use this board here. We'll use IQs again because we've done it before. So for IQ, again, the mean is 100 and the standard deviation we know is 15. Okay, 2 questions. Find the probability of an individual with an IQ between, I'm going to keep this simple, between how about 91 and 106. Okay, that's the first question. Second question. Find the probability of a sample of size, let's say n equals, I'll keep it simple, n equals 16. Find the probability of a sample size n equals 16 with a sample mean between same 2 numbers. 91 and 106. So the first question is, I'm going to grab an individual at random from the world. What's the probability that their IQ is between 91 and 106? Second question, I'm going to grab 16 people at random, find the mean of their IQs, and what's the probability that that sample mean is between 91 and 106? Will we get the same answer? No, because in the second one, we have to use the 16 in our calculation. Okay, so I'm going to show you how that works, because the second one is actually the way of the world. This is the most common way, because we don't do samples of size 1. Yeah, we do samples hopefully large. So let's see, what kind of erase this? Let me erase this. You guys all have this now. So let's do the first one. We've already done this before. In fact, I think I might have even used these same numbers last time we did this. So the first question is, what is the probability that an individual outcome is between 91 and 106? Remember, when we look at our Z table, do you have your Z table? Okay, when we look in our Z table, we're not going to see 91s and 106s. We need Z values. So I have to calculate the Z values. So 91, what's the Z value? For X equal 91, Z is what? 91 minus 100 over 15, right? Score minus mean over standard deviation. And what is this exactly? This is exactly what?
26.
You sure?
91 minus 100 divided by 15.
It's negative. That does matter. No, it's negative 0.6. Okay. You're not doing 100 divided by 15. You're doing negative 9 divided by 15. Now, you got to use parentheses on top. Yeah. Yeah, the one that you cannot do, you can't make calculator errors when there's that little going on. You have to enter parentheses. You're going to get the wrong number 100% of the time if you don't use parentheses. Now, what about for a X value of 106? The Z would be 106 minus 100 over 15. And what is that? I'm going to put 2. I'm going to go. Because when we look it up, that's what we have to look up, 2 decimal place values. Therefore, this question is the same as the probability that negative 0.6 is less than, so I have to erase this, sorry, is less than, Z is less than 0.4. Those are the values I'm going to look up in the table, right? Now, as a picture, what does it look like? All right, that's 0, so that would be negative 0.6, that would be 0.4, and I want that. Now, you don't have to draw the picture. I always draw the picture because it makes it make more sense to me. So what do? Remember, we take that probability, everything to the left of 0.4, and we subtract that probability, and that leaves us with everything in between. So what does that come out? What is the probability that Z is smaller than 0.4? I'll look that one up. The probability that Z is smaller than 0.4, that probability is what? Yeah, you guys all need to be doing this. There is nothing on planet Earth easier than looking up a probability when you're given the Z, but if you don't do it right 100% of the time, then you're guessing. Now, what am I doing? I'm now subtracting this probability, the probability of being less. So what's the probability of being less than negative 0.6?
2743.
2743. And so what is that difference?
0.3811.
3811. So this is actually very accurate. I'm going to grab a human being at random from planet Earth. Think of it that way. What is the probability that their IQ is between 91 and 106? It's the same as Z being between these two numbers, which is exactly this. So in English, roughly 38% of human beings have IQs between 91 and 106. Okay, cool. Now the second question, I'm not asking for an individual, I'm asking for an entire group to have an average between 91 and 106. That's not the same question. That's actually a little bit different because although those numbers are the same, what changes in the problem? I'm going to go ahead and let's see. I'm going to change the question. Because now the question is not X. Now the question is X bar. What is the probability that an entire sample is between? That is not the same because the calculation I do here is not going to be exactly the same. Now, there's going to be a z-score, obviously. Okay, and I need to do the calculation, but now it's going to involve X bar for both of these. So what changes in this calculation? I don't use sigma. Now what do I use? Sigma over the square root of n. What is n?
16.
Oh, so I go over square root of 16. Over square root of 16. What's the square root of 16? 4. So this is going to multiply my previous z-score exactly by 4. Oh. Now, when you're entering this in your calculator, you've got to use parentheses, folks, or you're going to get something goofy, right? Parentheses on top, parentheses on bottom. If I do that, then exactly what do I get here? Well, it's still negative. But everybody do it on your calculator because I want to make sure you're getting the right answers every time. Negative 2.4. Again, I'm going to put 2.40 because I have to look up 2 places. Whenever you're doing a z-value, traditionally, doesn't even matter the scenario, just traditionally people always go 2 decimal places on z's, even if that second one's a 0. And the reason is because all the tables that we use 2 decimal places. So it's more out of convenience. That's really big, isn't it? Now, what's the second one? 1.60. Gee, that changes things quite a bit, doesn't it? Now it's, I'm giving myself much room, negative 2.40, 1.60. Whoa. So I'm going to draw a different picture in a moment to show you how ridiculous that became. Let me go ahead and erase this. You have the question now. So let's look this up. So start with what is the probability? My new picture is negative 2.40 and 1.60. And I want all of this. Well, that's way more, isn't it? So what is the probability of being less than 1.60? Let's all look that up. 9452. Destiny is fast. 9452. And the probability of being less than, remember, we're taking all of this and subtracting that tail to get the meat in the middle. So when I look up the probability of being less than 2.40, what do we get? 0.00. Well, that's really small, isn't it? And this answer is 0.9370. Wow. That's a huge probability. What was our last one? 0.38 something? And I asked almost the same question. Oh, so that means that if I grabbed any group of 16 human beings on planet Earth, they're almost 94% of the time going to be between those two. What if I grabbed an even larger sample and even larger and larger? I could grab samples that are so big that I get almost all people are going to be in that range eventually. Yikes. See, the idea here is spread is much less. When you grab a sample, the scores are less and less spread. The larger the sample, remember I showed you, the more narrow it gets. So you're going to capture more things. So if I'm trying to figure out what is a reasonable range of values, this is not range rule of thumb, that's in a binomial experiment. But if I said, well, what is a reasonable range of values? You'd say, well, most outcomes we know are between 2 and -2 standard deviations. That's still the range rule of thumb. So if I said, I have a group of size 16, where are they going to fall? I can actually work backwards, just like we did before.
Just like a quick question. Are you recording or Zoom again?
Yeah, I am. Is he using? Oh, you know what? No, I think I might have accidentally clicked the Tuesday link. Have him go to the Tuesday link. That's my bad. Savina, you're on. How did you know to, I think I accidentally clicked the Tuesday link, even though it's Thursday. It doesn't matter from a recording standpoint, but it does matter getting on. Well, actually, most of you are here, but so central limit theorem in simple English says everything we did before we're still doing, but now we're going to divide the standard deviation by the square root of n, because the bigger the sample, the more narrow the outcomes are. And so the probability that an entire sample is way far from the mean is not real good. Entire samples we expect to be closer and closer and closer to the mean. Does that make sense? Now, what would a large sample be? Well, it kind of depends on the scenario. Believe it or not, most statistics books define a large sample, this is funny, as anything above 30. I just find, I'm sampling human beings. I want to find out information about grains of sand. 30 grains of sand doesn't seem like a very big sample, does it? Maybe 30,000 grains of sand. I want to, work with water molecules. I think 30 is probably not a whole lot, I probably would want more. The idea being whatever you can afford, time and money-wise. Now, if you said, well, it's free, what I'm doing doesn't cost money. I'm going to be surveying human beings. Great. But now it's a time issue, isn't it? So why would it be a time issue? We're going to do this when we get back from the break. We're going to talk about things like opinion polls. Why would time matter? Well, if there's an election, let's say in 3 days, I can't spend 2 weeks asking people who they're going to vote for and what they're going to vote on. I kind of need to do it, well, right now, don't I? If I'm trying to find out what people are going to do and the election's really soon, I need to do it immediately. Now, what if the election's 6 months away? Then I got all the time in the world. So in other words, does time affect your outcome? Yes, it can. Time can affect your outcome. This is one that I have fun with because I'm a big football fan. And last week was a really good week. Okay, I'm a Raiders fan. So the Raiders just traded for the greatest receiver of his generation. And I thought it was very interesting because I only have 2 channels on my TV that I watch, NFL Network and ESPN. I don't watch television shows. And what was very interesting, they were talking about gambling, which we have a little bit of familiarity with because of probability. And they were talking about how the odds and the things and, who's going to win the Super Bowl next year. Believe it or not, you can actually start betting on that now. Who's going to win next year? Because things constantly change. But the Green Bay Packers, I think, were the number 2 on the who's going to win the Super Bowl next year. And the Raiders were, not even in the top million. They said right after the trade, Green Bay fell out of I think they're not even top 6 anymore, 7. And the Raiders elevated to now, around 10th or something. Now, if you were doing this based on timing, you placed your Super Bowl bet. Then the trade happens. Do you get your money back? No. No. But would that change is it likely to change the outcome? Yeah, it could change the outcome hugely. The Denver Broncos, who are just a bad franchise, a bad team, and they were in the bottom 5 of Super Bowl favorites. And then what did they do last week? They acquired Russell Wilson, a Hall of Fame bound quarterback. And now all of a sudden, I saw something yesterday that has them in the top 10. I think that's a little too generous. Can time change things? Absolutely. So for those of you, again, I use gambling as an example. We call it insider information. You're going to play, we're not talking about cards where you have some control because you know the probabilities ahead of time. We're not talking about rolling the dice because you know the probabilities ahead of time. If it was an event that's about to happen and you're a gambler and you're betting on the game, okay? I'm a Lakers fan. Last night they played Philadelphia and there's a certain line on the game that one team is favored by a certain amount of points. And if you're a gambler, that's what you do. You say, okay, the Lakers are favored by 1 point. If I bet on the Lakers and they win by more than 1 point, I win my bet. If they don't win, or if the Lakers are favored by 6 points and they only win by 3, I lose my bet. They have to win by at least that many points, that kind of thing. Well, a lot of money is spent on these games. And then a couple hours before the game, they announced that LeBron James was not going to play. So if you're a gambler and you bet on that game, you're not a happy gambler because now there's literally no chance they're going to win this game. And they did. They made it close, but they didn't win. So we talked about insider information, right? Conditional probability. What's the probability the Lakers are going to win the game? And you'd say, you know what? It was a very good probability. From gamblers, they had a better than 0.5 probability that they were going to win the game last night. So you're a gambler. What is the probability they're going to win the game, given that you know LeBron James is not going to play? Now that probability goes way down. That's why I say time has a lot to do with things. Okay. Now I'm using a gambling example, but if I simply had waited a couple hours before I placed my bet, it would have changed everything. So when we're doing things and we're sampling in general, time is a huge issue, and so is money. We talked about sampling tires, right? Driving, by the way you test tires is you essentially drive them until they're worn out. There's no other way to test them. So a lot of times what they do is they'll have a test track and you'll just drive. I don't want that job, right? Your job is you're the driver on the test track. So you're literally going to drive a car for 12 hours and then get out and someone else is going to drive it and someone else can drive it. And you do this because usually a set of tires is going to last you several years, aren't they? But I need to wear them out as fast as humanly possible so I know how long they last. So we just drive them around the test track, and we might drive, you know, my job, I drive 1,000 miles around the test track, and then you take over for me, you drive 1,000 miles, and O'Shea takes over, you drive 1,000 miles. So we can wear out these tires in just a few weeks rather than 5 years, because we need to know how long they last. It's actually that simple in real life. But it costs money because I just basically threw away a set of tires. I purposely rode them to death, but I have to do that to know how long they last. This is true of everything on planet Earth that, you know, that you're selling and you're manufacturing. You have to know how long it's going to last. So you have to wear it out, which means you have to sacrifice it. Now, you'd say, well, the more tires you do, the better, because the more accurate your results. But if you're the tire manufacturer, you don't really want your sample to be millions of tires, because that means you just threw away millions of tires. So you have to figure out how many tires do I really need to sacrifice so I have a really good idea. I don't know what that number is. Maybe you determine it's 100 tires. 100 is a pretty good size sample. And if I have my drivers driving and that 100 sample, that 100 tires on average lasts a certain amount, then I could say, you know what? That's a pretty good number to use for the lifespan of all of my tires, because 100 is a pretty big sample. And again, the spread gets less and less and less. Okay, now we're going to take a short break here. When we come back, we'll do some problems. Let me stop recording. All right, so here's what we're doing. We're looking at problems 1 and 2 here, starting with problem 1. Given that the mean is 144.6, that's my mu. Sigma is 24.7, and my sample size is n equal 100. We're going to do exactly what we just did with the IQs before the break. Okay, so what is it we want to actually find? If I put it in words, I want to find the probability that X bar is bigger than 140. That's what I'm asking. That's the question. I can't look up 140 in the table. I need a Z value. So what is the Z value that I'm going to look at?
Negative 0.01.
Well, tell me what you did to calculate.
140.0 minus 144.6 divided by 24.7 over the square root of 100.
Beautiful. Now it's on you to make sure you enter it in your calculator correctly. Now, what did you get?
Negative 1.86. Negative 0.0186.
Well, sounds like there's disagreement.
Oh,
I got negative 1.8.
Is it 1.8 or 0.18?
It's 0.0186.
I think we might have gone the wrong way on the 100. So show me what you got. That divided by, no, that the denominator has to be in parentheses. 24.6 divided by root 100. That's what's in the parentheses. You put the parentheses in one place. Yeah. And by the way, this is why it's so important you guys enter this correctly in your calculators. So you got, all right. So if I say that I want the probability that a sample mean, this is a huge sample, size 100. What's the probability my sample mean is bigger than 140? You're saying it's the same as this. Now, whoops, sorry, not X bar, sorry. That's Z, is that what you're saying? Now, that I can look up. That's supposed to be easy. That's the quiz you just turned in. The quiz you just turned in had questions like this, and you just simply look it up in the table.
So it's over the square root of 100 because you want to get the variance for that, right?
Well, because that's the standard deviation of sample means. Remember, the variance of sample means was sigma squared over n. So the standard deviation is the square root of that, which would be sigma over root n. You remember we showed that before. Again, the variance of the sample means is this. So the bigger the sample, this is an absolute, the bigger the sample, the less spread. Remember the billionaire children example we did? The bigger the sample, we saw the spread of the numbers got smaller and smaller and smaller from high to low. So if I take the square root, then the standard deviation, which is the square root of that, must be the square root of this, which is that. That's where the root n comes from. Because it's in the calculation of z, you don't use variance, you use standard deviation, which is the square root of variance. Okay, so that's why you're doing it in this order. Now, this is going to be a really large probability, isn't it? So you're saying the probability of an individual being taller than 140, that's pretty big, but an entire huge sample being that tall, what's the probability? I go out and collect a sample and the entire sample is way below average or taller. You say, well, that's a huge probability.
I think I got a completely different number.
Well, it's physically impossible to ever get a right answer using any form of technology if you enter it incorrectly. You have a difference on top. If you don't put parentheses, nothing you write after that will ever matter. You have a quotient on the bottom. If you don't use parentheses, then it doesn't matter what you write after. So you have to enter this with parentheses. When you're writing it, you don't need it because you can clearly see it. But your numerator is the difference. So that numerator has to be done. And then your denominator is that quotient. So go parentheses on top, parentheses on bottom, way safer. So Destiny will tell you, if you don't use parentheses on the bottom, you're going to get a number that is the same digits, but wrong decimal places, right? And you don't want to do that. That's just crazy. So everybody needs to get the right number. It doesn't matter if you understand the problem, but not able to get it on your calculator, you know? Now, what's the next question? Oh, this is a betweener. It's the exact same question, but now you're going between those two values. What?
So what answer would we write? Would we write the negative 1.86 or do we write the...
Your answer is a probability. You haven't answered the question yet. You've now set it up, so now it's easy to answer.
So, okay.
You have to look that up in your table. You have to look. The idea is, the quiz you just turned in, I just said, all the problems on the quiz you just turned in look just like this, okay? And then you say, I just got to look up in the table and go, okay, is it 1 minus something? I'm looking up a number in the table and then either writing that number, if that's a less than or if it's greater than, I go 1 minus that. It's pretty darn easy. That was the quiz you just turned in. Today, I'm now asking you for a situation. You have to get it to this point. And now it's easy to just look it up in the table. That's the difference. Day one, we looked it up in the table. Day two, we said now the probability of an individual outcome, calculate, look it up. Now it's probability of an entire sample, but it's the same mathematics. I do the figure out what the Z is that I'm going to use, and then I look it up. Do I want you to what?
Do you want us to put the Z-score?
Do I want you to put the Z-score? Well, I haven't answered the question yet, but I can't answer the question until I do this.
Yeah, once we get that, do you want us to oscillate?
The question is, what's the probability? So you actually need to finish the problem. This is the meat and potatoes. I can't answer the question until I do this, but now once I do this, it should be easy to answer the question. Does that help?
Yeah.
So here's the question you're originally being asked, but you can't look up that question. You have to calculate the Z value. That's what we're doing down here. So what's the second question? So in words, what's the probability that my mean is between? And this is the second question. So now I have to calculate two z-values. Because the mean is 144.6, both of these numbers are below average, aren't they? What does that mean in terms of z? They're both going to be negative. Very important. We've made some mistakes subtracting in the wrong order sometimes. That is huge because you're now changing above average to below average or below average to above average. You never want to do that. Right? You already got that one? Oh. This is what today is. The only difference between today and what we did last day. Last day we looked at individuals. Today we're looking at entire samples. The only difference is dividing by square root of n in your calculation of z. That's the only thing that you're going to do differently. But you have to be mindful of saying, oh, how I do an individual and how I do an entire sample. Individual n is 1, entire sample it's bigger than 1. So that does affect my z. For those of you on Zoom, does anybody have any question on this? Everybody's muted with their cameras off. So I never understand the camera off part. It's funny because I taught classes through Zoom and I'd have a significant number of people that log on, turn off their camera and their sound. And I know for a fact they weren't there, but they thought somehow they're getting credit for logging into Zoom, even though you weren't required to because I recorded the lectures. But the people who logged on asked questions and interacted and stayed for office hours. The people who never turned on the camera went the whole semester without ever speaking, asking a question or anything. The only time I saw their faces was when I gave exams because they had to have the camera on them. And I had a couple who refused to turn the camera on. I said, well, then I'm not accepting your exam either. You know, it's not an option at that point. You got something meaningful? So except you only want 2 decimals, because that's what you're about.
Yeah.
Well, no, but you would round these to 12 because you're not looking at 6.4, you're not looking at 1.4. No, no, there's no such thing as rounding up, it's just rounding. Rounding means you're going to the closest value, not up or down.
So this would be 5?
That would be, it's closer to 6.5 than 6.4. That's rounding. Yeah. You don't automatically go up, you just go to closer.
What is it, the 5?
Well, if it's exactly a 5,
Yeah.
but you don't have exactly a 5. No, you have 5.7. That's still, is that, if you had 57 cents, are you closer to $0 or $1?
Rounding is multiple values.
I'm sorry? Well, no, you're not, you're calculating the z for that value exactly, and then you're going to restate your answer. Like you did here. You calculated this is now z, that's not x bar. This is now z. X bar is that number, and I calculate that z. So the inequality tells me I'm moving up here. The value I calculate is the value for this x and this x. So I calculate the z.
Yeah.
Does everybody have y'all have something meaningful?
You have to round.
You have to round it?
Well, you're only doing 2 decimal place values for z.
Yeah, I got 2.14.
Well, show me what you got.
Do you want us to round it though?
Yeah, you just hold it.
Well, okay, you're calculating a z value,
2.1.
and then you're looking it up in the table, but the table only has 2 decimal values. So if you have a 25 decimal value z, that's nice, but it's only, you're only looking up the 2 decimal values. So then
But
you
you
round
want
it.
us to, it's 2.145, so why wouldn't I just write 2.14?
Because it's not 2.145, it's 2.1457, blah, 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 blah. Is that,
So it's 2.145.
are you closer to 1.4 or 1.5?
1.5.
By the way, the rules of rounding are exactly the same in all situations in human history. Yet the funny part is I teach calculus students. They can't round to save their life. They never understood rounding. And rounding, there's no flaw. rounding. That's the problem, is people try to think. Rounding, let me just put a number down. I've got 3.4719546, blah, 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 blah. Okay. First of all, is how many places are you rounding to? There's no such rule as you always round. No, it's the situation. In my class, I have to round to 4 places. In another class, I have to round to 1 place. In another class, I have to, it doesn't matter. Okay, if I'm rounding to 1 place, what do I write? 0.5. The rule is absolute. If the next number is 5 or more, you go up. If it's 4 or less, in other words, 0 through 4, you round down, 5 through 9, you round up, period. But what if, no, period. That's it. It's never changed. It will never change. Now, if I'm going to 2 places, what do I write? 3.47, because the next number is a 1. Okay. If I said round it to 3 places, what are you going to write?
3.471.
No.
No, 2.
You're almost all the way to the next number. You don't, yeah. The problem is 99.97% of all human beings look at that number and that number only, and therefore they're absolutely incorrect exactly half the time. You're thinking, what is the next number? Is it bigger than 5? Yes, so it's 472. Now, here's where people get a little bit of trouble here. I want 4 decimal places. I want a 4 decimal place value. So what would I write? I want a 4 decimal place number. Am I more than halfway? So what do I write? 20. Exactly. Why would I write a 0? Because you're reporting 4 decimals. If you're going and you're paying with dollars and change, nobody says, okay, your bill is $3.4. No, they're going to say $3.40, because that's not the same as 39 cents or 41 cents. Nobody reports 1 decimal place. They say 40 if it's 40 cents. So yes, if you're saying 4 decimal places, the 0 is just as important as every other number. So if I'm rounding to 2 places, then the only thing I need to do is look at the 3rd decimal place. Is it 0 through 4 or is it 5 through 9? That's it. Don't do something weird and wonky and different than that. People do. Yeah, you don't say, oh, you always round in a particular direction. No, you round to the closest number. That's what rounding means. When you give me something meaningful. So you're saying, what Z values did you guys come up with? 2?
2.15, negative 2.15 and negative 0.40.
Oh, yeah,
No, the second one is negative 0.
What the hell did you use that? Yeah, how did you do that?
I mean, yeah, you guys are getting vastly different numbers here.
So the way I do it, because I get confused with all the
Oh, I know it. Never mind. She's right.
and everything.
What did
I
you do?
just do the top, so I do.
No, I know what you did. I put 0.0, not 0.6. So.
So you didn't square root it.
No, I did square root it. I didn't. I put 144.0 instead of 144.
Oh, that matters. So what did you get for that one?
Yeah.
Okay, that looks good. You don't want to make the calculations long. You want them to be short and sweet and simple. Except for subtracting in the wrong direction. That's going to be good. Remember, that minus that. You're going to have a negative number.
Oh.
That one minus that one. Well, okay?
Yeah.
Oh, okay.
I was just doing the wrong thing.
Oh, for the last.
So,
Yeah.
let's calculate the z that goes with this one. So for 139. Yeah. 139.3 actually equals just on this, the z. 144.6 over 24.7 over the square root. Yeah, so when you do it on the calculator, the parentheses here, parentheses here. So go open parentheses, you have close parentheses. 0.3. Minus 144. Score minus mean, it's going to be negative. 144.6. Close parentheses, divided by parentheses. 24.7 divided by square root.
Yeah.
0.4, and then we added another 0.
100. Press back, square root, 100.
Because all these words have both digits.
Close parentheses.
So we have from that too?
No. He was just saying like, they don't say they're gonna give you $4. It's because he says they're not gonna give you like $3.4
Next number is 5, and then go up, so
$3.
No, it's 0.2428.
That's your
Did you
Z.
subtract it though?
that's your Z value for this.
What did you subtract?
Oh, did you round? What'd you round to?
0.2586 minus
I'm now-
0.0158.
So what goes here?
Wait,
First one is
0.2.5.
5, and now
Is
So-
it 6?
So
No.
the Z scores we rounded to were negative.
This is fucking confusing.
Okay,
I don't think you rounded.
I know, but I don't think you round. I was always taught that if it does not say round, then you don't round. That is how I was
well,
always.
no, that's not the point. In the Z table, all your Z values are two decimal. No, those are probabilities. In your Z table, all your Z's are reported to 2 places only.
Right, so if
There's nothing wrong with reporting Z to 100 places. But when I look it up in the table, what value am I looking up?
but when I got this one,
That's where we.
2 places, I got 2.14 and then the
But
other.
the next number was bigger than 5, so you can't use
But it doesn't say
2.14.
round,
Doesn't matter.
but it does, that's how I was taught, it
No,
does
no,
not
no,
say
no,
round.
no. You're doing what's called truncated, which is never the right answer with a decimal. You never lop off decimal places, ever. That's, if somebody told you to do that, then they lied to you. They're trying to get your money. They're trying to sell you decent copy.
I was taught that all through high school.
No. You don't chop off the decimals, ever. No, if you say, I wasn't told to round, then you'd report the whole thing. But think about when you go to the gas pump and you're buying your gas. The amount you pay has been rounded to the nearest penny because you can't have a 3 or 4 or 5 decimal place dollar amount. Does that make sense? It's automatically rounded whether, you know. So if you're looking up a Z value, you can only look up 2 places. So you have to round it to the 2 places. You say, well, I'm just going to chop it off. But if you chop it off, you'll have the wrong number exactly half the time. So in other words, you don't ever chop off decimals. There is no scenario where that's ever the correct answer, to chop off decimals. You round it to the next place if you have to report it to 2 places. So you're never told to round, you're told to report it to 2 places. It's the same thing.
So if you had a 3-digit answer after you subtracted the Z-score value, you would just add a 0.
When you say that,
Okay, so I subtracted.
oh, right. Yeah, it's reporting, because otherwise it looks like you rounded it to 3.
I rather round.
Okay.
No,
No,
0
no,
and
yeah, okay, because I remember I turned in the last one and you said I had a couple.
You
3.
if it's a 4 decimal place answer and you only report 3,
No, yeah.
it doesn't matter. It always looks like you rounded to the 3rd place. If the 4th place is a 0, you break
Now
it
that I
down
get
because
that, it makes more sense.
rounding.
Because, like,
See, I redid the quiz, but
I don't
I added
know.
a 0.
I don't like decimals in general.
So when you're paying at the gas pump, you just give them whole dollars?
Yeah.
Remember, money is decimals too. GPA has decimals.
But I rather see decimals.
Here's the thing. You're working with a calculator. You're not having to do a whole lot, but you have to correctly interpret the results. So since our tables have z's to 2 values, by the way, if we were doing this on a computer, we wouldn't need to round anything. We just input the whole thing and then the computer would spit it out. But that requires that I understand the programming and I have to learn that language. There's a whole lot more involved in that. So we're looking up numbers in a table, but all the z values in the table are 2 decimal place z values. All the probabilities they're spitting back out are 4. That's why I said earlier in the course, if you have to give a decimal value for probability, you had to do a calculation. The rule of thumb most people use is 4 decimal places, partly because all of the table values are 4, and it's just convenient back and forth. Is there anything wrong with reporting a different number? No, but it's a practical issue. So if I'm using z values and I'm only giving you 1 place, and you look it up in the table, you go, there's 10 different z's that have that 1 place. Oh, that's why I'm giving you 2, so I can look up the right one. If we have a probability, we round it too much, then it's really hard to work backwards, you see. So if my z value has a 0 as the last digit, I still need that because that's what I'm going to look up in the table. So we have to be mindful that when we report or we're reading numbers, we want to be consistent. We want to make sure we're looking up the right ones. All right, let's go further here. Oops, here we go. Okay. Now, this one I looked up on the internet to get this question. This is kind of funny. Did you know that coins are not all identical? What? Did you know you can have a whole bunch of pennies that are not all the same weight? Now, are they going to be really close? Well, of course they're going to be really close. But because they're produced, bazillions at a time, you have some. Now, here's why that's kind of interesting. I thought this problem was interesting. I looked it up a few years ago. I don't ever use a vending machine. I can't honestly remember if I've ever used one in my entire lifetime. But I have had to pay, like parking, where you have to insert the dollar bills. Have you ever inserted the dollar bill and it spit it back out because it didn't like it? It was too crumbly, it was too wrinkly. So you're sitting there trying to flatten it out. Did anybody do this? Yeah, it drives you crazy. You're like, I don't have a brand new dollar bill that's perfect, right? Well, a vending machine, if you have let's say you're putting quarters in your vending machine. If you have a quarter that's just a little bit too heavy or a little bit too light, it might reject it. You see, generations before you, when I was a kid, they used things called slugs. You know what that is? It's a fake. Yeah. I have a fake coin. It's a slug. I have a fake coin that's roughly the same size as the quarter. It's roughly the same size, but it's not worth anything. And I use the slug in the vending machine. Yeah, the vending machine's not like reading the image. Oh, you don't have the right day. You don't have the right president on the front. No, it's actually completely by the weight. So people use slugs for years.
Actually, that's why the smaller ones, I think they kind of like scan it.
Well, nowadays everything's computer. But if I had a quarter, let's say, that was a little bit too light or a little bit too heavy, the machine may reject it because the machine is interpreting it as a slug. It's a weird phenomenon, needless to say. So this question says, okay, weights are normally distributed. They have this is typical. 5.67 grams is the mean. Okay, that's pretty specific, isn't it? But if I'm and the standard deviation is only 0.62 grams, 0.062 grams. But if I am too far away from that, again, it could be rejected. That's just crazy. It could be that. I just find that to be interesting. By the way, that is really small. That standard deviation is really, really tiny.
So what would be that?
What would what?
The N. We don't have an N.
Of course, what is the, well, first of all, a quarter.
So 1.
So the first question is 1. Okay, first question is 1. I just said a quarter is inserted.
Okay.
And then the second one, I'm saying 283 different quarters. So I think that's safe to say the N is probably 283. Now I'm asking what's the expected number of rejected quarters? Now this is a little bit different. So what's the if the probability of rejecting a quarter, let's throw out a number. Let's say the probability was 0.1. If the probability of rejecting a quarter is 0.1, then I would take that number and multiply it by my 283 quarters, and that's, right, that would be the expected number of quarters. So whatever your probability of rejecting the quarter is on the last question, multiply that by 283, and that'll tell you how many quarters are rejected. Right? That's the whole NP thing.
Oh, for the second part, okay.
That's the second. The first one should be really easy. But again, this is an interesting question because if you've ever driven and you had to insert the dollar bill to get the arm to go up and it wouldn't take your dollar bill, how that happened. And you're like, I can't leave the parking lot, I won't take my dollar bill. It's the same idea. Let's see. So it's 5. Okay. You don't have to do the square root, but that's correct.
Okay.
That is just 1.
Yeah, I just wanted to.
Yeah. So, well, it'd be square root of 1. So what's the square root of 1? 1. So that is correct, but you don't technically have to use it in your calculation because it's just 1. So it's a between one, right? So this is between here and here. Probably is between 5, 5, 0.
This is the first part of it.
Oh, okay. So what you always want to do, you always want to start off by saying something, what is it that I'm between, and then what is it my z is between. That way you know where the numbers are coming from. And you have to do a calculation. You're going to have to use a calculator. There's no way around it. But the calculations all look really similar, don't they? Something minus something divided by something.
My first semester at Mesa, I had a really nice one, and the screen was actually bright, so I could see it better. So I could see the numbers that I was putting in better.
So this one harder to remember?
Yeah, because the numbers are black. It's dark. It's a dark green background instead of a nice green. It's harder for my eyes to see.
No, I understand. I can't see the illumination on my dashboard, like the time and temperature. I have a very difficult time.
I miss my own.
Yeah, we have a thermometer in the house, on the wall and I have to stand at just the right angle. I can't read it most of the time. I have a difficult time seeing it.
My first year at Mesa, somebody stole it. I replaced it with a $100 calculator.
Which one do you want? No, that's the standard deviation. Question 3, your X bar is, or excuse me, your X, you're only doing 1. So this one's not an X bar. This is just an X. You're only doing 1. So X is between these two. So what's your Z between? Okay. That's less calculating on the first one. Now the second one, what is, just hypothetically, it's kind of a tricky question. What is the probability this quarter is going to be rejected from the machine? So you just calculated it number 1. Well, hold on. Whatever answer you got for question 1, that's the probability that your quarter is good to go. You have a quarter that the machine likes. If you are outside of this range by being too low or too high, your quarter is going to be rejected. Okay, everybody okay with that? So what is the probability of quarters in here? Let's say that number is 0.9. So then what's the probability it gets rejected? 1 minus that number. So your answer to number 3 is whatever it is, you're going to use 1 minus that number in the next problem, because now you want the rejected, not the number 3 is the accepted quarters. Number 4 is the rejected quarters. Oh, so if the probability of accepting a quarter, let's just 0.9, and the probability of rejecting would be 0.1. So whatever your answer to 3 is, start with 1 minus that for number 4. What was your answer? Now, this is the probability of rejecting an individual quarter.
And then you multiply.
That's my P, that's my N, it's the same P.
Multiply them over.
Yeah. So I got a big old, I just got done with one of the local casinos. I have my bucket of quarters. Literally, you ever see people do that? I have. They got their bucket of quarters. And so you left the casino with 283 quarters. And then you would have just start playing in the, well, you know, the slot machine not rejecting a quarter. Because it thinks it's small. Oh,
yeah. So
is it possible I'm playing a slot machine and the machine rejects a quarter? Yeah, it's possible.
What's 283 times 7?
And that's it?
And that should be, yeah.
Something like that, yeah. So what'd you get as an answer?
15.
Roughly 15 quarters. Now, this is kind of funny. This is kind of fun. Change vending machine to slot machine. So you're sitting at one of the local casinos doing the one bandit, and you had your big old bucket of quarters. You had exactly 283 quarters. Is that machine going to accept every single one of your quarters? No. Because you just said, you just told me how many of those quarters are probably going to be rejected because of
because you can't
great. So you're doing that, it doesn't accept it, you know, authorities come, they try to arrest you because you started. I don't know exactly what this is about. No, you can spend all the money you want. There's no limit to how much money you're allowed to spend. Yeah.
Basically, it's kind of like.
No, I have been, because I've been to Vegas many times. And I was just in Vegas recently for the rate of charge. And you're walking through the casino because they're everywhere. And at every slot machine, you'll see people sitting there and all of them have buckets. They don't pull change out of their pocket. They have buckets of quarters that they just keep feeding in the machine. Those machines are very hungry and they eat quarters all day, every day, as many as you can feed that machine. And occasionally, you know, you hear the ching, 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 you know, occasionally. All right. So hopefully this stuff made some sense to you. This is what we did today now is kind of the way things are going to be. Everything's about samples, not individuals. We have to start with individuals so we can figure out how to calculate things. But in reality, all statistics are usually based on samples, not on one thing. As we say, a sample of size 1 is kind of dangerous. To try to make a conclusion about the whole with a sample of size 1. You know, could you imagine you're watching a basketball game and you see somebody shoot the basketball. They either make the shot or they miss the shot. But you're going to base your entire, you know, your entire understanding of basketball or your entire scouting of that player based on the one shot. If they're a really good shooter, but they missed that shot, you're going to say, oh, they can't shoot because I saw them shoot once. If they're a poor shooter, I was watching the game last night and Dwight Howard was shooting free throws. Now, Dwight Howard historically is one of the all-time worst free throw shooters in NBA history. His career percentage is less than 50%. He goes to the line and the announcers have to say that. He shot twice, both swishes. Shaquille O'Neal, who was one of the worst free throw shooters in NBA history, the hack-a-shack, that was a strategy they used to use back in the early 2000s. In the fourth quarter, they'd just foul him constantly because he'd go to the line. I think he may actually hold the NBA record for the most made free throws in the fourth quarter. He had a game where I believe he made 15 free throws. Greatest free throw shooting game of his life. And they won the game simply because Shaquille O'Neal made all his free throws in the fourth quarter. Had they not fouled him, the other team probably would have won the game. So the strategy backfired because they based it on probability. Things can happen, but you can't do probability based on one thing. That's dangerous. You always want a sample, okay? So it's like saying, oh, I'm going to ask a stranger, who are they voting for president? And that person's going to win the presidency. I don't think that's a really safe method. Maybe I should ask 1,000 people who they're going to vote for. Why? Because tens of millions of people are going to vote. One person is not a very good way to make my conclusions. Okay? All right, let me give you your tests back if you'd like those. Okay. And the unclaimed test will just, usually I donate the points to Father Joe's charities. So,
Oh, that's
Junior, none of these people are actually here. O'Shea, Lila, Salvador, what's name? I'm standing in front of me. Robert, there we go. And Manuel, and you are my, and Andrea, and Salvador.
What you good?
Yeah, not too bad. Oh, thank you. You guys already know what you got. So, Lila. All right. Nice going.
Now, I am concerned, Jake, that you test not ready to take a test. Yeah, that's how it's.
Now, you get the drop test, but your first test wasn't good. Like, for example,
8 factorial divided by 0 factorial. You didn't even try it. Factorial and second permutation. So when we have it, I mean, we did these in practice problems, we did them on quizzes, we did them in practice tests. I'm concerned because this stuff should not have challenged you. It shouldn't, like 12, 2, 6. So you know. But that's the kind of stuff you got to get. So here's what I need you to do. I need you to fix some of these. I want you to try the test again. Now, most of the tests are sorry, no, over the break, at some point, redo this, break this, and see if you've got some of these. Because if you're going to continue, you've got to get some of these things. So this is more complicated than this. And it's not going to get easier. It's probably going to get more complicated. And I don't want to see you floundering around. I want to see you be successful. But right now, you're just not doing. You're not doing enough, obviously. So you've got to figure out how do you do more to make yourself more successful. All right, let me find this again.
In the last, yeah, I was doing math since like 5, 6 school year.